With him, Doug Hofstadter, we'll talk about curious patterns and non-patterns in a family of meta-Fibonacci recursions. Thank you for coming. Some people here are not familiar with the seminar, so let me remind you of two rules. One rule is for the audience: no electronic devices are allowed whatsoever, and no iPhones, and please silence, including the speakers. 2 weeks ago, a speaker had his own iPhone or cell phone ringing. So silence all your iPhones and no looking at, no texting, and that's the first rule. The other rule, unfortunately, I kindly agreed to break, is the upper limit of 48 minutes. Doug is a great guy, but he's on the long-winded side if you look at his books. So, 48 minutes. I kindly agreed to...
Would you kindly stop talking and let
Talk about long-winded. I've never had such a long introduction in my life. Okay. Well, I'm supposed to turn this on. I hope I can figure out how to do it. I don't know.
Yep, you're good.
Okay, now I'm supposed to go down to something.
Yeah, click on the qtheory.pdf tab at the bottom.
Oh, down there. Okay. Okay, so I click on that. Okay. Well, I didn't want to show that, but that's okay. It doesn't matter. We'll start out with a transparency. By the way, I don't like using these kinds of things. I usually like to write on the board or to just improvise. But in this case, there's so much visual imagery or things to look at that I thought it was necessary. So that's what I'm going to do. This all begins in probably something like the late 50s, as somebody might know. Mark Gardner wrote a column in Mathematical Games about a card game. It's not really a card game, but it uses cards, called Eleusis, which is a game where you make a pattern. I think it's a 5x5 pattern with playing cards, and then they're down and they're face down, and the person who's one person organizes them to make a pattern, and the other person tries to discover the pattern by asking for one card to be flipped, and by exposing various cards, they can perceive parts of the pattern, and they're trying to anticipate as quickly as possible what the hidden rule was. Now, I never played Eleusis, but I did appreciate the notion of the game, because it was described in the column as a kind of a seeking order, sort of what scientists do. They make experiments and they try to extrapolate patterns that they perceive in the world and to seek order. So I decided to make a similar game some years later that I called the function game, and I used to play it principally with one friend of mine, and it was a more mathematical game. I didn't like the idea of playing it with playing cards. So our idea was that we would write down a definition of a function of integers, then you try to make the function be as complicated have its behavior be as complicated as possible, but its equation be as simple as possible. The idea was that it would be hard that way to discover the rule if its behavior was very complex. But your score was how long it took your opponent. If you're the function inventor, it's how long it took your opponent, how many queries the opponent takes, divided by the complexity of the function. And the complexity was simply a measure of the expression where you attached points to each symbol and you summed them all up. And so there were, you tried to make a very simple expression so that you would have a low denominator, and yet a very complex behavior, so your opponent can say, what is f of 3, what is f of 7, what is f of 10, what is f of 100, and so forth. And that way they ask a certain number of questions, they finally get it, and then it's that number divided by the score of the function. So anyway, we played this game quite often, and I was exploring a bit, and one day I made up this definition for the function, a recursive definition. It was the first time I had actually attempted to use a recursive definition. And I found that it had a pretty interesting behavior. So this is sort of a picture of behavior. This is actually taken right out of GEB, Gödel-Schreiber, and it shows the behavior. Basically, if you can read these numbers, I don't know if you can, but for example, it's just saying that f of 18 is 11, f of 11 is 7, f of 7 is 4, and so forth. So it's just a descending thing. F of n is always below n. So both 7 and 6 have a value of 4. And this tree has a very simple structure. Aside from maybe a little bit of glitch at the very beginning, when there's a when it branches, it goes to the left and the right. It's only a double branch. There's never a triple branch. On the left side, it always branches again, and on the right side, it always has a tree or a trunk of height 2. And as soon as it gets to height 2, then it branches again. And then on the left, it goes again, and then here. And so it would branch here because this is height 2. Whereas it wouldn't branch here because this is height 1. Okay, so that was an interesting thing. And by the way, this, you'll notice here, 2, 3, 5, 8, 13, 21, the Fibonacci numbers go up the right side. So there was nice things there. And so I thought it would be interesting to generalize it. So I decided to try this function. And I came up with something that has a very similar tree. I've separated out the glitch here now, and so the basic idea is that you have now you have trunks of height 3 on the right instead of height 2. It's the same rule basically. It always branches on the left, and it always has a trunk of height 3 before it branches on the right. And so here it would not branch, and the ones that branch are written in red, so you can see that the 32 would because it's at the top of a height 3. Anyway, this is just sort of warm-up, but it's just giving you the sense that I was exploring these kinds of recursive definitions, inventing functions just to see what would happen. And so one day I invented this definition. Now in GED I called it Q, but my friend Greg Huber, who has explored these things with me, decided that it was, first, I can't remember why, he decided that Q was the generic name for a whole bunch of functions, and that this particular version, this particular one, would be called U. So I've adhered to his naming convention, so I've just called it U here. So it's a sum of two previous terms, and it looks like a Fibonacci kind of a thing because it refers to the previous term and the term 2 earlier, but those are inside. This is subtracted from n, and those two differences become the arguments, and those are the terms. So what it amounts to is, if I go ahead one slide, I think I can show this to you, is that if you want to know what the next term is, you take the previous two terms and you just count back those two numbers. So let's count back 9 and 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So you take those two terms and you add them and you get 11. And that's the next term. And you keep on doing this. Now, at first it looks as if it's going to be monotonic, but here it becomes not. It goes backwards. And so it turns out to be a very kind of chaotic, unpredictable sequence. And I was, at the time I invented this is about 1963, I was programming, and so I wrote a program to explore it, and I looked at the behavior, and I will show you what it looks like. So here are the first 120 terms, roughly. And what we just saw was down somewhere along here. What you'll notice is that I put some things in red, and the reason I did that is that it looks as if there is, well, let's go over here. There is a period of stability, and then an explosion. and this is like 6. There's 6 red dots here, stableness. Here, this is at, this explosion starts at 96, 3 times 2 to the 5th. So there's 6 terms, 6 constant terms right before that. If you go back to 3 times 2 to the 4th, which would be 48, that's this point here. There's a similar explosion that starts at 48 with 5 terms before it. Then if you go back to 3 times, well, half of 48 is 24. So there's 4 terms here, and this is the 24th term right there. And then similarly, there are 3 terms here, and this is 12. There are 2 terms here, and this is 6, and there's 1 term here, and this is 3. So there seems to be a very curious kind of behavior in which there is a complete stable plateau at 3 times, just before 3 times the power of 2, and then a kind of a crazy chaotic explosion. Well, this is very, very curious behavior. This shows it continuing, going out to about 500. What I wanted to say is that the pattern is broken after this. It turns out that this is not exactly stable. It's not. It doesn't have. This had 6 red dots. This does not have that many. This has about 8, but one of them is at a different height. And so, in fact, the pattern is broken. But what remains is that what remains of that pattern is that there's a sort of a calm before the storm. There is a kind of an explosion at 3 times the power of 2, but there's a kind of a calm, but the calm is not as simple as it was as it appeared, which was a disappointment to me. Of course, I was hoping that it would be a absolute perfect thing, but it wasn't. Now, one thing that let's go on look a little further. This goes out to 10,000. This is going out to 10,000. And you can see how it looks. It really gets very chaotic, but you can see that it has this chaos which then kind of converges, and then it explodes and converges again, and it explodes and does that each time. Very peculiar kind of a behavior. Since it is so unpredictable, it's predictable but not predictable in some sense. Since it is so crazy, it's very hard to prove anything about it. And one thing, nobody has ever proven that it exists for all n. Why would it not exist? Because if q of n minus 1 or q of n minus 2 becomes too large, then when you subtract it from n, you get a negative argument, and that's not defined. We don't have. I mean, of course, you could define it. You could just arbitrarily give it, say all the values of negative arguments are 0 or something like that. You could certainly have it continue to exist. But the way it was originally defined, it doesn't exist for negative arguments or for 0 argument. And so the question is, does it continue to remain below n? Because if it doesn't, then it will die. And asymptotically, it seems to be about n over 2. And if you knew that it had that limit, you can prove it easily. But if you knew it had any limit, it follows easily that it is a half of n. So that's a fact. Now, I think I have a further graph just going out to 100 million, just so you can see how it looks if you go out to 100 million. These things, these sausage things, keep on going. And it's been explored numerically by a number of people, Greg Huber and myself, and a mathematician, or I think he's a physicist in Germany named Klaus Pim, and probably the people who have looked at these things the most, and I'm going to talk about generalizations, are a group led by Steve Tanney in Toronto, at the University of Toronto, in the math department. He's had a lot of students, one of whom is John Chu, but I think he's had a number of other collaborators. And I should mention that they are the people who probably know the most about this class of functions, Tammy and his group. But Greg and I have explored some interesting things that I don't believe, I mean, everybody has their own take on what's interesting here, and they generalize it in different ways. So, yeah, that brings me to this one. I had forgotten see, I don't like transparencies. I don't like a transparency here to talk, but anyway, it doesn't matter. This is a variant of it that I invented in about, I don't know when, but sometime in the 60s or the 70s. Now, what I found was that as I generated the terms, and I did them all by hand, I don't know why, but at that time, for some reason, I no longer had any access to a computer, so I just generated about 100 terms by hand, and I found fairly quickly a recursive rule. I wish I had had the time to show you the tree. There's a tree that, like the first two trees that I showed you, there are trees that there's a tree for this function that looks very similar to those. It's a little more complex, but it's not much more complex. And it explains the structure of this function completely. And I found it, I don't know how to say it, sort of disappointingly simple. And so I just put it into a drawer and totally forgot about it. Well, in about 1990, I don't know the exact time when it was, I was in an airport flying somewhere, and I got the copy of the New York Times, and I opened it up, and there was an article that said, John Conway loses a $10,000 bet about something in mathematics. So I started reading it, and it said Conway had made up a function, and it had this definition. Now, can you imagine in the New York Times to have that in the New York Times? I was just blown away, but I didn't recognize it. I said, gosh, that reminds me of my old Q function. It reminds me of my old Q function. And then it said Conway had thought that it was so chaotic and so crazy that he bet that he gave a $10,000 offer to anybody who could explain the behavior of this function. And so as I looked at it, I thought, gosh, that's so close. These things, by the way, were named by somebody meta Fibonacci because they involve the idea that a preceding term or terms being added, using the a of n minus 1 to tell you what to do with add two previous terms. So it's kind of Fibonacci-like. Well, but it's 2 levels down, so that's the meta Fibonacci aspect of it. So I was intrigued, and then it said that Colin Mallows, a mathematician at Bell Labs, all this takes place in the strange state of New Jersey, if any of you have ever heard of it, by the way. He had analyzed the behavior of the function and published a paper on its behavior. And so I was intrigued, and the more I thought about it, the more I thought, why didn't I ever invent this function? And it seems so natural. So then I went back to my files, and I have very good files, and I opened up my files, and I found these little sheets in which I had scribbled things in pen, and I saw that I'd calculated the first 100 values, that I'd made this tree and everything, and that I considered it to be sort of trivial. And so this was a weird thing. So I wrote a long letter to Conway and to Mallows and told them about it, and I never got an answer from Conway. I did get a very polite answer from Colin Mallows, who was extremely nice and who acknowledged my priority, which he didn't need to do because I had never published it. He just, actually, I was very flattered that somebody would actually want to kind of share credit with me. So now, if you look in certain websites and things, you'll find my name attached to this function. I mean, of course, Conway's too, and Mallows too, but my name is there too, and I'm very delighted. And I think, though, that in fact, Conway got the idea from GEB because it was written, the other one, the U function, was in GEB many, many years earlier. And so I'm assuming that he just kind of was inspired by that, and he told his biographer, whose last name I've forgotten, Siobhan, I can't remember right now, she also wrote the biography of Hofstadter. You know who I mean?
Roberts.
It's Siobhan Roberts. He told her that he had gotten the idea from Key Dewdney, but Key Dewdney doesn't seem to have anything to do with it. I think that what he meant was the person who wrote, who took over the column after Martin Gardner, which was me, and then Key Dewdney took it up somewhat after me, and so I have a feeling he just blurred us in his mind. So anyway, so I guess that you know, it's just an interesting thing. The behavior of this function looks like this. It looks very regular in some sense, and if you subtract n over 2 from it, and then graph it, it looks like that. And you can see that it is actually extremely regular, this perfectly symmetrical bump, which consists of little sort of fractal bumps on top of it. And that's the behavior of it, more or less. And I'm sorry I don't have the tree to show you the way of analyzing it with the tree. But anyway, it gives you a sense that it's not so mysterious after all. It's extremely regular and very easily defined. There's nothing chaotic or bizarre about it. It's sort of a closed book. So
in particular, you had a proof of Conway's conjecture?
I did not.
Ah.
No, Mallows did.
Yeah.
No, that's why I said it was very generous of Mallows. I didn't send him, I sent him a letter in which I stated that I actually showed how I'd analyzed the structure of the sequence, which was very different from
But you conjectured the same thing.
Oh, yeah.
Conway.
Oh, yeah.
Yeah.
Yeah. Well, I didn't have to. Well,
Mallows' proof was wrong, you know.
that I don't know. That's interesting.
That was 96.
The prize was for the first time the average got within some distance of something. And Conway thought this would be far too big for anyone to ever possibly compute. And Colin thought that it was some number around 1 million or something. The actual number is very small, it's a couple of thousand.
Interesting. Okay. No, I didn't remember those details. Yeah. Okay. So, I looked at some generalizations. Greg Huber and I decided we would explore generalizations of what I call the U sequence. And so we invented this one, the V sequence, which needs 4 values to get off the ground, because you have to have something defined for up until n minus 4 becomes positive. And so we just decided to give it these initial values. So here's what it looks like. Up to 10,000. Here's what it looks like up to 1,000. But this is what it looks like when you look a little more fine-grained. Between 100 and 300, it's a little bit bumpy, as it turns out. And this is what it looks like between 0 and 100. And you can see it is actually, it's a kind of a staircase that either is, going up at these angles of 45 degrees or horizontal, 45 degrees horizontal, and so forth. And the question is, what is this pattern? Now, Greg and I worked at trying to understand the structure, and with our friend Kelly Gutman, who was very interested in exploring it with us, the 3 of us were able to find a recursive pattern. I mean, the definition is recursive, but what I mean is a simpler recursive description of the order in it. And once again, I don't have that. I mean, I have it more or less. These are the block lengths: 4, 1, 1, 1, 2, 2, 1. This is sort of a way of encoding what is. Let's get back for a moment. So this is, I guess, 4, 1, 1, 1, 1, then a block length of 2, then 1, 1, then 2, and things like that. So you get, that's this a way of encoding the pattern in the graph, and this pattern can be explained more or less in the following way. That is, if you take, for example, the terms that begin at 40 and the terms that begin at 80, what you do in order to get these are the terms that begin at 80, broken up into little groups. In other words, that sequence is just 1, 3, 2, 2, 3, 2, 1, etc. So what the rule, the pattern is that you can get these, the lower ones, from the upper ones if you obey these rules. That if you and you have to take these in sort of backwards order. That is, first look for all 2, 2, 2, 3s. If you see one, replace it by that. If you see one of these, replace it by that. Then take shorter sequences. After you've taken out the 2, 2, 2, 3s, there still could be some 2, 2, 3s. Replace those by that. Replace these by this, and these by this, and these by this, and these by this by this, and this by this. And that's the full rule that'll give you the next generation. Then when you have that generation, then you apply it again, and you keep on going. And that's the complete analysis of V. Now, Greg, after a considerable amount of work, was able to prove that this was the case. I know that it was not a very satisfying proof. It was just kind of grinding it out in a certain sense without any deep insights into anything. It was frustrating to him that he couldn't, there was no central idea of the proof. What I know is that Steve Tanney and his collaborators have generalized these sequences in different ways. And they also have published a number of papers in which they prove various properties of these sequences, similar to these in some ways. And their proofs also, I know they're very frustrated with their own proofs. They have the same complaint, that there are no central, large, deep ideas. They're just kind of deep analysis of cases, but not interesting. So there's still the hope that there might be some kind of deeper insight to be found. By the way, I had said that I was going to offer some monetary prizes. I better not forget to do this. One today, and that is, I'll offer a $500 prize to anybody who can prove that the U sequence exists for all n. This has been out, I mean, the question has been out publicly ever since GEB came out, which was 1979. And that's, 35 years. And it hasn't yet been proven to exist for all n. So I feel fairly comfortable in offering a $500 prize. I wouldn't want to go too much higher than that, but I'm happy to do that. So, all right, now this is the more obvious, the obvious generalization that Greg and I found. This is not the family of functions, I believe, that Steve Tanney and company have explored. For some reason, they've explored different variations on the theme, and that's fine. But this particular family mostly belongs to Greg and me to some extent. Maybe other people have explored it too, but I'm not familiar with other people exploring it. The initial conditions don't have to be all ones. We're assuming that S is larger than R, because since it's symmetrical. Let's just assume that R is the smaller number. So S is the larger one, so we'll just set all of the first S terms equal to 1. You can have other initial conditions, of course, but we've explored only 3 patterns for the initial condition. No, we've explored 4 patterns for the initial conditions. I'll come back to that a little bit later. But this is the most, probably the simplest set of initial conditions, or at least it's a very simple set of initial conditions. And so what kinds of things can happen? So let's take these particular values for 2 and 4. We call it W because it doubles the 1 and the 2 that U had. So 1 becomes 2 and 2 becomes 4, so W is this function. All right, what does this look like? It looks like that. The sausages have gone away. It just becomes a pure chaos, but it does look like it goes on forever. And this is going out to what, 100,000? I know it's been explored much farther than that. So it looks as if this one